This lesson illustrates how to solve a linear programming problem using the simplex method. This is a linear programming problem with three variables, x1, x2, and x3. We don't count the z. And two constraints. The constraints are x1 plus x2 is less than or equal to 5, and 3x1 plus 2x2 plus x3 is less than or equal to 14. In every linear programming problem that we will be discussing, all the x variables are assumed to be greater than or equal to 0. The type of linear programming problem that we first solve is called a standard maximum problem. What makes it maximum is that we are maximizing z. What makes it a standard maximum problem is that among constraints, all of the inequalities are of the less than or equal type. And the numbers after the inequalities are greater than or equal to 0. Those are the conditions that make up a standard maximum problem. Our goal when using the simplex method is to transform this linear programming problem into a system of linear equations. We begin with the first inequality, x1 plus x2 is less than or equal to 5. We make that an equation by adding a non-negative variable to the left side called a slack variable, so that the inequality will now become an equation. That is, we will add s1 to the left side so that x1 plus x2 plus s1 will equal 5. For example, if x1 were 1 and x2 were 2, x1 plus x2 would be less than or equal to 5. The slack variable s1 would then be equal to 2. The next inequality, 3x1 plus 2x2 plus x3 is less than or equal to 14, will also become an equation by adding a second slack variable that we will call s2. So we've converted the second inequality into an equation. Next, we write the z equation down and then transform that. What we're going to do is transpose all the x's on the right side of the equation and bring them over to the left side. The z equation now reads negative 2x1 minus 8x2 minus 3x3 plus z equals 0. It's very important that you make the change in the z equation in this way. The x's must all be brought over to the left side of the equation through subtraction. We have a system of linear equations. There are 3 equations in 6 unknowns. The 6 unknowns are x1, x2, x3, s1, s2, and z. The equation containing the z must appear last in this system. Recalling the Gauss-Jordan procedure, you see that this is the matrix that will result from that system. Ignoring for the moment that the x's and s's have to be greater than or equal to 0, whenever a system has less equations than unknowns, there will never be a unique solution. If there is one solution, there will be infinitely many. Let me show you how you can get one solution to this system. Let all the x's be 0. If x1, x2, and x3 are 0, then looking at the first equation, it is clear that s1 will equal 5. From the second equation, s2 will equal 14. And from the third equation, z will be 0. How can you see that solution from the matrix? Notice that the x1, x2, and x3 columns each have more than one non-zero number in their respective columns. The x1 column has 3 non-zero numbers, 1, 3, and -2. The x2 also has 3 non-zero numbers in it, and the x3 column has 2 non-zero numbers in it, 1 and -3. The other columns, S1, S2, and Z, have only one non-zero number in each of their columns, and that one non-zero number is 1. Whenever a column contains more than one non-zero number, the variable for that column is set equal to 0. And that's how we can see x1 is 0, x2 is 0, and x3 is 0. S1 will be read by looking at the row containing the non-zero number, that's the number 1 in the S1 column, and take the ratio, the number in the last column divided by that number. So S1 will be 5 divided by 1. S2 will be 14 divided by 1. And Z will be 0 divided by 1. That's how you can read the solution from the matrix. It's important to note that x1, x2, x3, s1, and s2, all the x and all the slack variables, must be greater than or equal to 0. We begin with the initial simplex table. We will be pivoting on one of the numbers in a row above the last one and in one of the x or s columns. Through successive iterations, we will reach the solution giving the maximum value of z. I will now explain how to find the pivot. First, we'll find the pivot column. Look at the numbers in the last row under the x and s columns. Those numbers are called the indicators. The column containing the most negative number is the pivot column. The most negative number is -8, and therefore the x2 column is the pivot column. We next want to find the pivot row. The pivot row is never the last row. The pivot is never in the last row. To determine the pivot row, we look at the ratios of the numbers in the last column divided by numbers in the pivot column. The first ratio is 5 divided by 1. And the other ratio to consider is 14 divided by 2. The row containing the smallest positive ratio is the pivot row. Those ratios are 5 and 7. Therefore, the pivot row is row 1. The pivot is the number 1 in the first row, second column. To pivot, we apply the procedure we learned from Gauss-Jordan. We want to get a 0 where the 2 is and the 0 where the -8 is in the x2 column. We will change row 2 using row 1 and row 3 using row 1. there are the correct row operations to get the new rows 2 and 3. Look at the indicators in the new matrix. There's only one negative number, the negative 3, and that is therefore the most negative number. It's in the x3 column, and so the third column is the pivot column. Looking at the ratios, 5 divided by 0, that's undefined, and 4 divided by 1, that's 4. There's one positive ratio. Another way to look at that is that 0 is never going to be a pivot. So the only positive ratio we have is 4. It's therefore the smallest positive ratio. And so the number 1 in the second row, third column, is the new pivot. We already have a 0 in the first row in the x3 column, and so we want to get a 0 in the third row where the negative 3 is. That's the result of pivoting on the number 1. So the row operation to do that is row 3 plus 3, row 2. Now notice that there are no negative numbers among the indicators. This indicates that we're done and that we've reached the maximum value of z. Let's read the solution from this matrix. There are 3 columns containing more than one non-zero entry among the variable columns. The x1 column, the s1 column, and the s2 column. Therefore, x1 equals 0, s1 equals 0, and s2 equals 0. x2 equals 5 divided by 1, or 5. x3 equals 4 divided by 1, or 4. And z equals 52. The solution to this standard maximum linear programming problem is therefore read as follows. The maximum z equals 52. This occurs when x1 equals 0, x2 equals 5, and x3 equals 4.